Join us today for a webinar where we're going to discuss pH 201, sensor technologies. They're not all created equal. This is the second in a series of sessions on pH. If you like what you hear today, plan on attending our next session, which will be announced soon. Today's presenter is Jorgi Day. Jorgi has spent the last 20 years providing field support for analytical instruments and sensors for customers and industries around the world. In her current role as Senior Analytical Product Specialist for Honeywell, she's been in just about every industry helping customers like you get the most of liquid analytical measurements. Jorgi has worked at TBI Bailey and ABB and has a Bachelor of Science in Chemical Engineering. Because of the large number of attendees, the lines will be muted. If you have a question, please use the chat tool that's built into GoToWebinar. With that, Jorgi, I'll let you take it away.
Thanks, Mike. Good morning, everyone. Welcome to the webinar, and welcome to pH 201. This is going to be a presentation on how on the pH sensor technology. There's many types of pH sensors these days. There's a lot of different technologies. We'll do a couple review slides just to make sure everyone has the right background, and then we will proceed on. So this is a review slide from last time. If you attended the last seminar, hopefully you'll remember this. Just a quick review on how a pH sensor works. pH sensor is like a chemical battery. It's a voltage source. It generates its own voltage signal. It has two electrodes, a measuring electrode and a reference electrode, plus a temperature sensor. The measuring electrode is either made of pH-sensitive glass, or it's an ion-sensitive field effect transistor. And it is responsible for the span and response of the sensor. So if you put your sensor in a 4 and a 7 buffer, but it only measures 4.5 and 6.5, that means that you have a short span, and that's a symptom that there's something wrong with the glass measuring electrode. It's also responsible, again, for the response. So if you put it in a 4 and a 7 buffer, it reads correctly, but it's slow responding. That is also an indication that there's some issue with the glass. The reference electrode is there to maintain a constant voltage to be compared to the changing voltage of the measuring electrode, and it completes the electrical circuit. Without the reference electrode, you can't have a complete circuit. And it's responsible for offset. So if you put your pH sensor in a 4 buffer and a 7 buffer, and it measures 4.5 and 7.5, that means it has a perfect span of 3 pH, but has an offset of half a pH, and that would be related to the health of the reference electrode. Okay. So this is just a quick picture of what a pH sensor looks like and how it works. You have your pH-sensitive glass on the measured side. You have a silver chloride wire, and then you have a buffered pH 7 solution inside the glass. So when you put this glass into your fluid, if you're at 7 pH, it will generate 0 millivolts across the glass because it's 7 pH inside, 7 pH on the outside. If you put it in a 6 pH solution, it will generate 59.15 millivolts. In a 5 pH solution, 118 millivolts, etc. So it's 59.15 millivolts per pH unit. So as this is changing, the signal goes to your transmitter or your analyzer, and we call that a high impedance voltmeter. You can't just hook a pH sensor to a millivolt source, because like a multimeter, and try to read it, because it's a very high impedance measurement. It has a lot of resistance in that glass, and you only have picoamps of current flowing, so you get a little current loss. You don't get the right signal. So that's why you have to have a pH analyzer or a pH transmitter. So it goes through this high impedance voltmeter, and then it's connected again with a reference on the other side. The reference is, again, a silver chloride wire. It's in a electrolyte of potassium chloride. That's the KCl. And then you have a porous liquid junction, usually ceramic or Teflon or some other porous material. And that allows electrical connection between the two. Okay. So let's go ahead and take a look at the technology of pH sensors. Believe it or not, there's still replaceable electrodes available, sensors that have replaceable electrodes. There's a variety of manufacturers that make them. What you're seeing here is a Honeywell device. It's a 7773. This is a 1960s and going forward technology. You have 3 separate electrodes, and this was kind of put together early on based on laboratory style sensors. So they're all 12 millimeter, and you can see a picture in the top right-hand corner. The leftmost one is the measuring electrode. You can see the pH-sensitive glass on the bottom. The center one is your temperature compensator, and the right-hand one would be your reference electrode. So they're the same components that you would have in what we would call a unibody construction, which is what most people are familiar with, but they're separate electrodes. So if one dies, you can just take it out and replace it. It comes in a large bell housing. Housings are at the bottom right-hand side, and these may or may not contain a preamplifier in the top. The issue with these, it's nice because you can actually replace a single electrode, like the measuring electrode if that's what's crapping out in your process, or the reference electrode if that's what's having a problem. But you have all these O-rings to deal with and whatnot. It's a little bit of a complicated process. And they tend to be a sedimentation trap in your process because you have those 3 electrodes hanging out, and then you have this protective cover on them. And so if you have a process that tends to crap things up, it's definitely going to get stuck on these 3 sensors. And it was just sort of a pain in the rear to replace the electrodes. So as time went on, and we got better at making pH sensors. Oh, sorry, part 2, I forgot. So part 2 is for high purity water pH. And actually, high purity water requires 3 separate electrodes because high purity water has to have a flowing reference, which means that we're using a liquid potassium chloride. And you have a reservoir that holds that potassium chloride with a tube going down into the reference electrode, and then the measuring electrode on the right. You have a temperature sensor in the middle that also acts as a solution ground to take away those streaming voltage potentials which you get in high purity water, because high purity water doesn't have very many ions in it. So you have to have that solution ground. You have to have a 316 stainless steel flow cell so that you can take that to a really good earth ground. The inlet and the outlet are offset so that you don't get a siphoning action off of the outlet. If you have one of these and it's siphoning, you can usually tell because it will suck up the potassium chloride faster than it should. And then, of course, we have the very large reservoir on top, which makes this an ideal sensor for measuring high purity water. And you really have to have it. You can't use something with a gel reference. You can't use the unibody construction because it just uses the KCl too fast. That's such a small volume. So you have to have this for high purity water, but it's not a very good sensor for any other application. So the replaceable electrodes are mostly used in power plants for high purity water. So if we go down and have a look at measuring electrode technologies, you'll find the, again, oldest, I'm going to go oldest to newest. These are all out there. A lot of people are still making spherical glass, which means it's basically a ball of glass on top of a small Pyrex stem, a cheap, inexpensive glass stem. So the active sites on the measuring electrode are on that ball. It has an extremely large surface area, which is nice because the surface area relates to how long the sensor lasts in terms of how many active sites you have that the hydrogen ions can land on. So it has the largest surface area, and so therefore the most active sites. However, it's very delicate due to its physical construction. It's very easy to break the glass either by mishandling, say in a beaker when you're doing a buffer calibration, or just in the process. These tend to have lower temperature ratings and lower pressure ratings to keep the impedance down. So they're not quite as tough against high temperatures, high pressures, and they're not really happy in really extreme pH applications as well. The next one up is the hemispherical glass. This is a pretty decent picture of hemispherical glass. So basically it's a half of a ball or a half circle, and it is welded or annealed to, again, a glass stem. It has the second largest surface area, so it still has a lot of active sites, but not as many as the spherical glass. This is the strongest shape, and the reason it's the strongest shape is because if you think about this half ball being welded to a hollow glass stem, that weld angle is 180 degrees. And that is going to be your strongest angle. So if you have like a really high temperature, or if you bump it, it's going to be less likely to break along that weld line. It has the highest temperature and highest pressure ratings for a glass measuring electrode. And most of the pH sensors that I see out in the processes are hemispherical style. And that's probably because it is the most robust. It's not always the right one for your process. You know, this all depends on your process conditions and your application, etc. But this is, I would say, the most robust of the glass measuring electrodes. The next one up is flat glass, and everyone in the industry was really happy to see flat glass come along, because if you have a process that is highly coating, or it has maybe a lot of particulates and it's moving swiftly through the pipe, it's easy for a hemisphere, and especially for a sphere, to get broken hanging out there in the process, even if you put some notches to protect it, etc. So flat glass is wonderful for those types of applications. Unfortunately, it has a smaller surface area, obviously, because now we're down to a disc instead of a hemisphere or a sphere. But it is the least likely to break in your process because it's not hanging out. It has a flush profile with the liquid junction and the body of the sensor. I would also consider it the cleanest profile because, again, it doesn't have anything sticking out that your process may tend to crap up on. So it's not going to get coated up usually as quick as a hemisphere or a spherical glass. These are typically good only up to 100 degrees C. Some of our hemispheres go up to 140 C. In fact, in a different body style, we can actually do 150 C, which is really, that's the highest temperature rating in the industry. But anyway, good till up to about 100 degrees C. And the reason for that is, again, that weld line where the actual pH-sensitive glass is welded to the stem wear. And that weld angle is 90 degrees, and that is going to be the weakest of the weld angles. So a high temperature, when the fluid behind that glass starts to volatilize, when you get over the boiling point, that can actually cause it to break right along that weld line. And this is pretty typical for what I would consider good quality pH-sensitive glass. And that kind of runs across the board for most manufacturers. Okay, so our last pH measuring electrode technology is the ifset. Ifset stands for Ion Sensitive Field Effect Transistor. It's a little piece of an electronics put into a little plastic body, and has some layers in it so that it's protected, and then it's all melted and heat sealed. It's non-glass, which is wonderful because you can put it in the process and it won't break. It's unlikely that you would break it during a calibration. In fact, you know, sometimes you can even drop it on the floor and it doesn't break, which is pretty nice. It doesn't wear out. A FET doesn't have a set of active sites that are being used up by hydrogen ions. It's actually creating a field, and it counts hydrogen ions coming through a gate in that field. So it's not going to wear out. It can be damaged by some process fluids, but when you get in the middle range, I would say that you're probably in pretty good shape of not having it damaged. It has a very low impedance signal. It doesn't have that high impedance that a glass pH sensor has, so that means it's going to be more stable in terms of electrical noise getting on it. You've probably had times when you've seen your pH sensor get whacked out, and maybe it's due to some high voltage valve or pump or something nearby. And the really slick thing is it's about 10 times faster than glass, and that's what this little diagram is in the bottom right-hand side. That green line is a FET sensor. The white line is a good quality glass pH sense electrode, and they were both put in a buffer at the same time, and you can see how quickly the green line gets up to the actual buffer value. It takes about a second for the FET to get to its value when it's brand new. For a brand new pH sensor with a glass measuring electrode, it takes about 10 seconds, which is not slow. I mean, that's pretty much what everybody sees, but a 1 second response time is pretty astounding. And I have on this slide that we are the experts, and the reason we're the experts is because when Honeywell bought Leeds and Northrop, they bought the, Leeds and Northrop is where our analytical line came from, and Honeywell bought Leeds and Northrop back in the mid-90s. Leeds and Northrop developed and patented the industrial FET, and we call it the DuraFET. That's our trade name for it. So we've been doing FET technology since the mid-90s. We really have a great grip on it. And we make a very nice FET sensor. Okay. So that's some measuring electrode technologies, and that's important in terms of matching it up with your process, depending on, you know, if your process craps up a lot, if it's thick or a slurry, or if you have particulates, if you need a particularly fast response, you know, and also depending on what your pH range is going to be. The next side is the reference side, and the reference side has a couple of components you want to look at. We want to look at the liquid junctions, and then we want to look at the formulation of the potassium chloride in the reference itself. And that's important because a lot of pH sensors die because the reference gets poisoned. And this is all important in determining if you have the right technology in your process, or if you can tweak it a little bit to get longer life, less cleaning, less calibrations, etc.
Jorgi?
Yes.
We do have a question, and one of the questions that came up is, what's the downside of the ISFET? You may be getting into it here, but I just wanted to make sure that we had that covered for one of the members.
Yeah, no, that's a good and timely question. The downside to the ISFET is that it's not, it's like Superman. If you expose him to kryptonite, he just goes down. So with a FET, there are some applications where a FET will work. I've never seen it not work. It's just a matter of how long. If you put it in hydrofluoric acid, the hydrofluoric acid is going to remove the protective coating on the face of the FET, and so then it will count all the ions instead of just hydrogen ions. So it'll immediately go up to 14 and start flashing. So the downside with the FET is only, well, there's two downsides. It sticks out. It's not a flush technology. And so because it sticks out, if you have something that really craps up a lot, you might have to clean a FET more. But the real downside is lifespan. In an environment where it doesn't have any chemicals in the process that are going to go after the materials protecting the FET, that measuring electrode will last forever. It doesn't wear out. But if you have something that's going to cause a chemical attack to some of those materials, then it will kill the sensor. And that may be in a shorter period of time than a glass measuring electrode, or a longer period of time. You know, and then you can start getting down to the bits of minutia of what's in your process and your temperatures and pressures. And then folks that do what I do have to figure out, is this going to be a better technology or worse technology than glass for your process? So that's the answer to the FET question. So go ahead and head back on to the reference electrode technologies. And the first order is the liquid junctions. Liquid junctions are simply a porous material of some sort. It can be anything from a hole to porous ceramic or Teflon or Kynar or even wood. There's sensors out there that have wood liquid junctions. The liquid junction is really important because it allows electrical contact between the process, the measuring electrode, the process, and the reference electrode, because current has to flow through the sensor for you to get a reading. And if you lose electrical contact, you lose the current, and then you don't get a reading. So, and there's a variety. The most common I see out there is porous ceramic, and I think that's also the oldest material. The second most common is probably porous Teflon. I like the porous Teflon because the pores are a little bit smaller, and you can get them a little more irregular when you dope the Teflon and burn out the doping material. You just fire it out, and then you get all these holes in there. They're teeny tiny holes. You can't really see them. Porous Kynar, I haven't seen really good results with that. I've seen a few sensors with porous Kynar. They tend to get plugged up. Wood makes a good liquid junction, but it is susceptible to chemical attack a lot of times, so you have to be careful where you put that. So my vote is for an overall material. I like porous Teflon, followed closely by porous ceramic. And with the liquid junctions, the size of those holes or the pores is very, very important, and the size of the junction itself. And that's important because, yes, you want to keep electrical contact, but you don't want process fluid to go into the reference area and mix with the potassium chloride in there, because it changes the voltage potential around the reference electrode, and that causes an offset in your sensor, and you'll see it as drift in your measurement. You keep calibrating down, down, but the sensor keeps going up, up, and that's a drift problem. That's a poisoning problem. Also, if the holes or the pores are too big, then that allows potassium chloride, depending on its formulation, to get sucked out of the reference area. And if you don't have the potassium chloride, you lose your electrical contact at the reference electrode. And of course, you're just surrounded by air, and so you don't have a stable voltage potential anymore around the reference electrode. So the smallest of the frits would be the smallest of the liquid junctions would be a frit, and a frit is just terminology for a very, very small hole. And if you look at some laboratory sensors that are completely glass, you'll see the measuring electrode, and then if you look up on the side, you'll see a tiny hole in there. And that hole is that's your liquid junction, and it allows you electrical contact. And that's really a nice liquid junction for a laboratory type sensor, because a lab sensor goes into something nasty for just a few seconds, measures it, comes back out. So it's not likely to get damaged very quickly. But if you put something with a frit in the process, because it's one single small hole, it can get plugged up. But usually, more often, what happens is process fluid gets in there, and it gets in fairly quickly and kills your sensor fairly fast. The standard liquid junction, which you see on maybe something like a Rosemont tough pH sensor, Great Lakes 3-prong pH sensor, trying to think of who else. Those two in particular, I'm thinking of just right off the cuff. The liquid junction is still pretty small. It's a porous material. I think they use porous ceramic. And that liquid junction is about the size of a regular pencil eraser, if you remember regular pencils. Most people use mechanical these days, but pretty small. The next size up would be what I would call a medium-sized liquid junction, and that would be similar to a Durafet or a Meridian. It is an annular liquid junction, which means it goes all the way around the measuring electrode, which is a much better way to do that. It gives you a little more balance and less issues with junction potentials. So that would be like a medium-sized one that is like a little annulus that goes around the measuring electrode. And then the largest liquid junction would be similar to something on what we call our HB sensors. And that liquid junction starts at the outside of the glass measuring electrode and goes all the way to the inside of the body of the sensor. So it is the largest liquid junction. In most processes, I like that very large liquid junction because there's less chance of coating and plugging up the sensor. Okay. If we look at the formulations, yes.
There's another question. What is the availability for electrodes specific to other ions? And he specifically says calcium ions.
Oh, boy, you know, that's tough. Less than 1/100% of specific ion applications are actually not pH. pH is a specific ion, although we don't call it that. It's keyed to hydrogen ions. But like calcium is tough. Probably the most readily available is chloride, followed by fluoride, and then you have a whole laundry list. There are very few manufacturers that even make those electrodes anymore because, and it's sad because it's it's a very, very, very tiny portion, and that's why it's not very profitable for manufacturers to make them. A lot of times, depending on what a customer is looking for, Honeywell makes the standard. We do chloride and fluoride. I think that may be the only two at this point. I'd have to go back and look. I just see so few of them. But it's bad because, you may have one of those in your plant and then a whole pile of pH, and you want to do, all the same analyzers, et cetera. And that makes it difficult. But the availability of those is very small. There's a few manufacturers that actually make that measuring electrode, probably a handful, probably no more than 5 or 6 in the world that make those, and then they sell them to all the various, what I would call the big guys, like Honeywell, ABB, Great Lakes, Yokogawa, all those guys. And some manufacturers provide more and some provide less. I think we're down to 2 styles. I think it's fluoride and chloride. Calcium's going to be tough. If whoever's asking the question wants to pop off an email to Lesman and myself, I can get you some names of places that you can get them. But one other, as an aside, one other little thing about specific ions are that they have lots and lots of things that interfere with the measurement, and a lot of times just throwing it over the side into your tank or your process, you don't get a real measurement. It requires a lot of different stuff.
Great, thank you.
Welcome. Okay, so let's see, single junction liquid potassium chloride. So now we're talking about the internal of the reference, where the reference electrode resides. And there's a bunch of different formulations of the potassium chloride. Something like 99.6 or 7% of all pH sensors use potassium chloride as the electrolyte, as the current carrying fluid. And I mean, that's just pretty standard. Unless you have a very odd process, you're going to be able to use potassium chloride. The liquid technology is the oldest technology. Basically, it's just the saturated solution of potassium chloride in clean water. And it's a good technology for mild applications where you don't have a high temperature, you don't have high pressure, and the pH is maybe 6 to 8. The reason being, again, because your process fluid is going to want to go into and mix with the potassium chloride in the reference area of your sensor. And if it's a liquid, that's going to be the easiest for that to happen. So if you keep the, if you're in a process pH of 6 to 8, there's nothing weird in there, no strange ionic species. You can usually get away with having a single liquid junction and a liquid potassium chloride. Now, the next step that was taken in this technology was to go from a single junction to a double junction. And basically, it's still a liquid junction. This is a little bit newer technology. And what happens is, instead of just having your liquid junction at the front of the sensor, they'll have a tube with potassium chloride with that liquid junction, and then they'll have a second tube inside. So it's completely enclosed with the second liquid junction. And I've even seen triple junctions. And the idea is that the junctions slow down the migration of poisoning process particulates and ions into that area, because once you get process fluid around the reference electrode, the sensor stops having a stable voltage. You start seeing drift, and you have to throw the sensor away. So there are a lot of double junction. There are a lot of single junction and double junction sensors out on the market. This particular one is with a liquid, and I wouldn't recommend it beyond 5 to 9 pH. And folks, these guidelines of, if I give you temperatures or pressures or pH ranges, those are just general guidelines. It's kind of a starting point. If you have some, weird ionic species in your process or some chemicals, then the 5 to 9 pH or the 6 to 8 pH may not even be a good guideline, because it could attack and mix with your particular sensor technology. The next one up is the differential pH sensor, and I spent an hour the other day trying to find a picture of the inside. I know I have one somewhere, but I just couldn't find it, and I was all over the net looking for one. A differential pH sensor is called a dual high impedance sensor, and it's a more modern technology. That technology comes to mind. The major manufacturer would have been Great Lakes, now part of Hawk. I think they invented the differential pH sensor technology, and this was a step up from having a double or a triple junction with a liquid KCl inside. And the way that works is you have your pH measuring electrode sticking out of the sensor just like normal, and then inside your sensor, instead of having potassium chloride, you have inside you have potassium chloride, and then in the potassium chloride you have another tube. And in the second tube is a buffer solution, and inside the buffer solution is a second pH sensor. So dual high impedance refers to having two high impedance sensors, the pH measuring electrode that measures the process and a pH measuring electrode that's sitting in a buffer. And the idea is that as the process starts to poison the potassium chloride and then starts to move into the area, number one, it gets diluted by the potassium chloride, and then as it moves into the area where the second pH sensor is, it's moving into a buffer solution, which of course is designed to hold its pH, and so that slows down the attack on the reference. It is a better technology than using a pH sensor that has a liquid fill inside if you're in a process situation. The downside is that they're expensive because they have two full-on pH measuring electrodes in them, and they will only work with a instrument that's designed to function with a dual high impedance or a differential pH sensor. They're appropriate for mild to moderate applications, low to moderate temperatures and pressures, what I would call easy to moderate pH, which is between 5 and 9 as well. Again, there's exceptions on those numbers always. Okay, the next one up is the gel-filled potassium chloride reference, and that is probably what I see out there more than anything else out in processes. It was a huge step forward. Between the liquid fill and the gel fill, the industry went through what's called a slurry-filled reference electrode fill. And that slurry was an attempt to, of course, make the fluid thicker so that process fluid couldn't get in, less compressible, it's harder to mix, etc. So it was a real boon when manufacturers came out with this gel technology. Not all gels are created equal. Some gels don't do well with elevated temperatures and pressures. Some do better. I can tell you that the gel in some of the Honeywell sensors that use the gel technology is a gel that will not change viscosity throughout the whole temperature range of the sensor. But some gels do change, so you want to kind of keep an eye on that if you're going to use a gel technology. Again, this is the most common technology, and it's appropriate for moderate applications, so medium temperatures and a moderate pH, say 4 to 10. Now, I've seen these put into applications that are less than 4 and greater than 10. It just depends on the chemistry as to what will work. But again, that's probably the most widely applied type of fill. Next one up is a polyacrylamide. There's a few manufacturers, there's actually small manufacturers, not what I'd call one of the giant ones like Honeywell, that manufacture polyacrylamide reference. And that's kind of a sort of a squishy, soft plastic. It kind of reminds me of styrofoam, except it's really dense. And it hangs on to the, and these are all still potassium chloride. This is just a different formulation, physical formulation. And this is a good fill for applications that tend to get into a little bit higher temperatures, a little bit higher pressures, moderate pH, again, 3 to 10. It's still going to have the same issue for chemical attack as the other types of fills, including, the double junctions, differential technology, etc. But again, you can see that as time goes on, manufacturers are coming up with technologies that are getting more and more resistant to the terrible things that happen to pH sensors when they get stuck in a process. The last technology up is the HB reference technology. This is a picture of a ball valve insertion style HB sensor. The HB reference technology is really best for harsh environments. It will work in any situation except for high purity pH. And I'm going to show you a little drawing of how it works. These have the highest temperature pressure ratings in the industry. They can go as high as 150 C in a particular body, which we only manufacture as a special. Our regular ones go up to 140 C. And they have the highest pressure ratings in the industry. If you put it into what's called a pressure monster body, which is a stainless steel or Hastelloy or titanium body that threads into the process, it's not ball valve insertion. I did an application for a downhole oil application, and the pressure was, we rated it to 5,000 PSI. And there's not a pH sensor on the market that goes that high. That's really crazy. It'll easily go 0 to 14 pH. Now, when you get, the farther away from 7 you get with any pH sensor, the shorter its life's going to be. But this particular sensor technology in the reference is going to, when you get into nasty environments, is going to have the longest comparative life to, say, a gel technology, the polyacrylamide, all of those other ones that we talked about. And of course, it's going to be, this technology is going to be more expensive than, say, a liquid-filled potassium chloride, because there's a lot more that goes into it. So I'm going to give you a quick overview of this. What you have inside your tube, where your reference electrode lives, is instead of a gel or a slurry or a liquid or polyacrylamide, etc., what you have is a bunch of wood sections. The front one, there's a front piece that's Teflon, and then you have 5 wood sections, and in between these wood sections, there are wooden dowels that have a hole drilled in the middle for the glass stem to come through. And in between each of these wooden dowels is a set of Viton seals, and these seals are sized such that they seal, one seal seals up against the glass, but not against the body, and the other one doesn't seal against the glass, but it does seal against the body. And one of the seals has these little pads, these little slits in it right along this one on the right, and the current flow from one dowel to the next dowel is through, it goes up against the body, goes down one of these slits, and then goes up against the glass into the next chamber. So you have these little chambers made out of these wooden dowels, and they are completely soaked with potassium chloride, and then this entire device is built under the surface of the fluid. So once the dowels are soaked up with potassium chloride, the saturated potassium chloride, they never see air again, and that's important because air, as well as process fluid, air is more mobile in a reference than process fluid is, and it can quickly cause a reference to become unstable, just like poisoning can. So what this sensor does is it keeps process fluid from getting to the reference. And the reference electrode, and I forgot to put it in this drawing, my apologies, but right here at the back would be the reference electrode. It's 50 times the size of a standard silver chloride reference electrode. It's all the way at the back, and it's well protected. So if you were to take this sensor and put it next to any of those other technologies and just put it in a plain water application, it will probably have the same lifespan as any of those other technologies, because the lifespan in that application is going to be based on the active sites on the glass, how soon they wear out and get coated up, etc. But the nastier the process gets, the better this technology looks. So let's say you put this technology next to any of the other ones in, say, a lime scrubber in a power plant. This is going to, I've seen it last, well, I did a test with it when we first came out with this, and it was first against the Great Lakes in this application. The Great Lakes was lasting 2 weeks. Then we put in a what we call our Meridian, which is a gel-filled reference. The Great Lakes was a differential. We put in a gel-filled, and it lasted 4 weeks. We put in a DuraFet, so then we switched from the glass to the FET, but still a gel reference, and that one lasted 6 weeks. And we put in our HB test sensor, was the test sensor at the time, and I know this is hard to believe, but it was installed for over 9 months and still running when I had last checked on it. I think they ended up giving it the heave-ho somewhere around 12 months. So we went from the best we could get out of a gel reference was 6 weeks, that was the DuraFet, to 12 months. So that's pretty awesome. It's really great technology. These devices come with a glass, currently come with a glass measuring electrode. So, and here's the tagline on reference technology. You can't always afford to buy, you know, the HBs of the world for your process. I mean, and if you have a really easy process like, you know, drinking water or, you know, treated municipal wastewater, something like that, you don't really need this technology because it's only going to buy you a little bit at best. But it will work everywhere except for high purity water. But here's the deal. 95+% of all process pH sensors die because the reference gets compromised. 95% is a lot, which is why you see all these, you don't see very different measuring electrode technologies, but you see a lot of different reference electrode technologies, because that's the weakness in pH sensors is the reference electrode. And so that's what manufacturers have gone after over time. And this HB technology is a patented technology. And the good news and I have to put a little advertisement in here, this will make my boss very happy, but it'll make me happy too. Coming soon, we have taken the HB reference technology and the DuraFet measuring electrode technology, and we've put them together. And it's going to be called the HBD. So it's the HB reference technology with D meaning DuraFet. So that's going to be the model for the new pH sensor. And we're currently in beta test right now, and we wanted to do a release in September, but we're not going to hit the September date. We're hoping for maybe November. And that's because so far they're still not dying. And we need them to die so that we can, you know, have a feel for how much longer they last than a regular HB sensor, how much longer than a regular DuraFet, etc. But I think this is going to be awesome technology. I started this project myself. This was my project six years ago, and we finally got money for it, and we're producing it, which is very cool. I'm really excited about it. So, what do you use for your application? Well, if I could give you a list that would answer all of those questions, I would not have been doing this for 20 years, because that's a lot of what I do is help people choose what sort of technologies are going to be best for their process. In general, if you have high purity water, you need something like an HPW 7000, which is our high purity water device that has a flowing reference. It's made of stainless steel. It has good mixing chamber. It has a solution ground to give you a very stable measurement. And that's really the only thing that will work in high purity water. High purity water is any water that is less than 20 microsiemens conductivity. If you're in a municipal water or wastewater, gel-filled reference works great. Those are very mild applications. Hemispherical glass is good because it gives you the most active sites, and they're not real challenging. Industrial wastewater, a gel works pretty well with a Durafed or an HB, either one of those. And you know, it just depends on what's in the wastewater. I mean, some industrial wastewater has hydrofluoric acid in it, and some of it, I've had industrial wastewater that started at -2 pH. I mean, it was pretty nasty stuff. When you get into the chemical, petrochemical business, oil, mineral processing, even like the sugar manufacturing plants and the ethanol plants, I'm starting to see a lot of HB use in those applications. And soon we'll have the HBD, which I think is going to be a real help to industry. Okay, and then I threw in a few pH troubleshooting tips, but I'm not sure how our time's going because I'm not good at looking at the clock, but that's Mike's job. But hopefully you guys will have some questions that I can answer readily over the phone about troubleshooting. I'm happy to answer as many questions as you want to stay on and ask. But here's just some general tips. And the first one is I tried to list 3 things that I see happen a lot. And I see a lot of ground loops out there. You know, you may have like a mixer or something in your tank, and it may have a faulty ground that's been in there for a long time, and that can cause voltage to be in the process that doesn't belong. The pH sensor, because it's generating a millivolt signal, it expects to go to instrument ground when the signal comes through. And if you have voltage in the process that doesn't belong, if your process is not at earth ground, that forces extra current to go through the sensor, and it gives you a wrong reading. So a lot of times you can have a pH sensor in your process, and say your process is 9 pH, but it's reading 11 pH. And you're like, well, that's no good. But you take it out and put it in a buffer, and it seems to read correctly. The test would be to pull a sample of your process and put the sensor in that beaker, a glass beaker or a plastic beaker, something that's insulated and isolated, and see if it reads the process correctly. If it does, what that means is there is a problem with the insulation. There is some voltage in there that doesn't belong, and it's upsetting the pH measurement. And you would see that with any pH sensor. A Durafed would be a little less susceptible to it, but only a little, because we're talking still about a pretty small signal. But the test is to put it in this beaker process fluid. If it reads correctly, the odds are really, really good that you have a ground loop. The other thing you can do is you can take a ground strap and take it to earth ground, a good earth ground, and drop it in that beaker and see if the reading jumps. If the reading jumps, that means you definitely have a ground loop. There's voltage in the process, and you're going to have to figure out how to get rid of it. And a lot of times it's something that has lost, some other thing that's lost its ground. If the reading does not jump when you do that test, that doesn't mean you don't have a ground loop. It's only a positive test. It's not a negative test. Another issue I see is the pH sensor gets stuck on a value and doesn't move. And we all know that in a live process, your pH is not going to be 7.8 all the time. It's going to move a little bit. So if it's not moving, the first thing I would do, of course, is make sure that somebody hasn't put the instrument in hold, because it may be holding that value because somebody's done something with it. But more than likely, it could be broken glass. Symptom from broken glass is either, because what happens is when the glass breaks, then you get a dead short between the measuring electrode and the reference electrode. And so then it just sticks on a number. And it won't be, a lot of people say, oh, if it sticks on 7, it's broken glass. But that's not necessarily true. I've seen them stick on all kinds of weird numbers. It doesn't really matter, because once the glass is broken, the internals start getting flooded with process fluid, and that changes all the voltage properties in the sensor. So it won't necessarily be stuck on 7. It could be stuck on anything. You can't always see broken glass. If you have a sensor that you have threaded into line and somebody has used a pair of channel locks on it to tighten it or to loosen it, that twisting motion can cause the glass inside, that glass stem that runs the length of the sensor, to get a little tiny crack in it. You'll never see it because it's inside the sensor, but it will, over a small amount of time, create a liquid path between the reference, which surrounds it, and inside the glass where the measuring electrode is. And when that happens, you know, it sticks on something usually. So you don't want to ever use channel locks on your pH sensors unless you're just taking it out to throw it away. Noisy pH readings. Noisy pH readings are oftentimes caused by entrained air. Lots of processes have air bubbles in them. It's pretty common. And air bubbles, because they're lighter than the rest of the process, will float to the top. So you don't want to install, just as a matter of course, you don't want to install a pH sensor, say at the 12 o'clock position. If you're in a horizontal pipe, and if you think of it as a clock, the top is 12. If you install the pH sensors directly in the top, and you have entrained air, all those bubbles are rising to the surface, and you can't measure the pH of a vapor or of air. You have to be in a liquid with these devices. And what it does is it gives it a no signal pH signal, no signal pH signal. So what you see is the pH jumping all around because it's trying to measure air and it can't. So with that, let me go to the last slide and entertain all of your questions.
All right, Jorgi, we have a question from the audience. What's the best probe for corn mash?
Corn mash.
33% solids.
Oh my gosh. Can you give me a description? Can you give me a description of something that I might know is the same consistency?
My guess would be somewhere in the beer making process where there's the mash.
Okay.
I think the customer is in the ethanol field.
Okay. I've done some, I'm going to try and relate it to corn. I have.
Yeah, here you go. His response is the first step slurry of an ethanol plant. Which is
okay, all right. So I have an application where I actually gave Rosemont the boot, I'm happy to say. And it is in, I don't know if it's that very first step or the second step, but it's a really, it's a very thick slurry. I can't remember if the pH is either really pretty high or pretty low. I can't remember which because it's been a couple of years since I've been back there. But it's really nasty. And what we did in that plant was we used an HB sensor with a flat glass. The flat glass, of course, to keep things from crapping up on it so fast and getting just kind of trapped and stuck, just material stuck on it. So with the flat glass, the sensor is in the side of the pipe. This is actually an upflow pipe. So the sensor is just stuck in the side, so the flow is at 90 degrees. And it's the HB technology. The reason it's the HB technology is because we determined that it was a reference issue in terms of the actual full lifespan of the sensor. And they've, I think, tripled their lifetime by going from the Rosemont Tough pH, which I didn't describe. Their reference technology is just like a little corkscrew tube full of potassium chloride. But I think we went like around 3 times the lifespan. Now, the other thing that we had to do in that application was set up some automatic cleaning, because even with that flush, flat profile, the sensor would still get crapped up like every day. They would have to take it out and clean it once a day for sure, if not more often. A lot of times they were doing it once a shift. So what they did, because we don't have, because this is a ball valve insertion style, so you could take it out and, you know, test it and all that, and calibrate it. What they did was they inserted these little tubes with hot water, and the tubes go out into this pipe, and they probably stick out until they're about maybe 1.5 inches from the face of the sensor. And the sensor has a lock on the back, so you can only push it in exactly as far as it's supposed to go in. And so I think every hour this device just squirts hot water onto the face of the sensor. So that was something that the plant actually designed, this little tube. And we hooked it up using the relay contacts in our UDA 2182 in our analyzer, and it actually runs it because we have a washer timer function in there. And so what it does is when that washer comes on, I think it comes on for like 15 seconds or something, not very long. While that is on, it holds the output so that no chemicals get dosed in based off reading this hot water instead of the fluid, the process fluid. And then once the water shuts off, it still holds that output for another, I don't know, 10 or 15 seconds so that the sensor can recover and come back to the real reading before it starts controlling it again. So we used an HB with a flat glass, but they also put in this little cleaning tube on each of the sensors. And they make a triple redundant measurement. So they actually have 3 ball valve insertion sensors in this one pipe, just kind of stacked on top of each other, with the 3 little tubes to clean it. And they've had really good results with it. They seem to be real happy with that. So that would be the direction that I would recommend.
Expanded on that just a little bit and said that they use the pH probe to determine the cleaning ability of the CIP.
Oh, okay. So they're CIPing and they want to know if it's
yeah.
Okay, that's tough.
It might be worth a little offline conversation, and I'll look him up and we'll make sure that we
okay. Yes, clean in place is a whole different animal. There's a whole variety of problems and issues that come with that. But yeah, we can certainly take that offline.
Great. At this point, I don't have any further questions. Jorgi, thank you very much for your presentation. If any of the audience does have any specific application questions, they can feel free to give us a call at 800-9-LESMAN or 800-953-7626. If you don't know your account manager, feel free to ask for me, Mike DeLaCluse, and I'll make sure that you get taken care of. Pay attention to your email. We'll be sending one out shortly on our next webinar regarding liquid analytics. So stay tuned for that announcement. At this point, if I don't see any further questions, we'll conclude the presentation. Jorgi, thank you very much.
Thank you, everyone.